a bunch of the experiments for us as well. So what I'm going to do is I'm going to talk a little bit about the sort of the motivation of the paper, and then I'm going to turn it over to Kevin to talk about some of the experiments, and maybe Kevin and I will switch it off for that part of the presentation. And I guess I'd like to see. I'm new to Discord, but I'd like to see if we can try to keep it interactive. If people can just sort of, interrupt me with questions, or or if there's something you feel like we're not going to talk about, then we can talk about that, skip ahead to it, or something like that. We probably have a lot more to talk about than we have time, and so it'll be better if it's interactive, because then it'll make sure that we talk about things that people are actually interested in. Does that make sense?
That sounds great. We usually get lots of questions and stuff, so not to worry.
Excellent. Okay, great. Okay, so here I'll dive in now. Okay, so the project we call it Rome. Looking at editing factual knowledge in GPT. It's on archive. There's a little project website. You can see all about it. Click through that. We have different materials you can play with while we're going through the talk. So the problem is it's an interpretability project. The question that really drives the project is the simple one, which is this drive to understand what it is that a neural network knows. What does my neural network know, and how does it know it? Now, it's sort of a funny question. It might seem vague, but it's actually a pretty important question that is getting more important. And it's really becoming more important because of the rise of unsupervised training. It used to be that AI models really only learn what you taught them and carefully labeled, but now that unsupervised learning is starting to really work, we're starting to get AI that is learning things that we didn't really explicitly teach them. And probably the most striking example of that is the autoaggressive transformers like GPT models. So as you all know, transformers invented by Ashish Vaswani at Google a few years ago, and they're really good at imitating real text. There are a lot of good open source implementations, including your guys' work. To program them, you just show it some text like this. So here we've grabbed 40 gigabytes of web text, 27 million pages. You train it just by exposing the model to this text and using standard optimization methods. You can use a GPU to speed up the training process. It still might take a few weeks to get it done, but in the end, you get this marvelous object, a trained network. Here, I'm showing you GPT-2, which was trained exactly with this type of data by Alex Radford at OpenAI a couple years ago. And it has about, this model had about 1.7 billion parameters. And so it's a big model, but it's conceptually simple, right? It's just a function. As input, you just give it a series of words. It does a bunch of arithmetic, and as output, it produces a prediction, right? A guess of what the next word would be. So here, in this example here, I'm showing here, the input is Edmund Newport performing on the, and then as output, the word that GPT predicts should come next is the word piano. And I'll put a little green check mark next to the word piano here, because actually Edmund Newport was a famous 19th century pianist and composer. So in a sense, this is really the right word to put here. And it makes you think, oh, maybe GPT knows some things, right? And you see a lot of these amazing sort of predictions come out of the model. Here's a few more examples of musicians. If you say Miles Davis plays the, in purple, we'll have the prediction, trumpet. I don't know if you ever heard of Niccolo Paganini, but it's true. He was a master violinist in the 19th century. And Jimi Hendrix, a little bit more contemporary, right? He is a virtuoso on the guitar. That is also true. So there's all these things that are remarkable, because even though what the model is doing is it's just sort of producing predictions of the next word, they seem to capture a thing that we think of as like abstract knowledge. right? So, for example, there's all these knowledge graphs where people have tried to catalog, all the factual knowledge on the planet, and they're generally expressed as fact tuples, right? Relationships between a subject and an object through some sort of relationship. So it's sort of like a fact tuple for that fact at the top would be Edmund Newport is related to the object piano through the relation plays the instrument, right? And somehow, you wonder, does the model actually know this fact? Now, as you can see, there's actually a lot of ways of saying the same fact. But you could use any of those ways to probe the model's knowledge. But then there is this funny gap between knowing something and just saying it, right? And so let's do this. So this is actually an exercise that Elazar did last year, which is to probe a fact using a lot of paraphrases. So here's Edmund Newport performing on a virtuoso on is known as a master of the favorite genre. So if you look at these completions, now you start to realize, well, maybe GPT is not so smart, right? If you use different wording, instead of saying that he is a virtuoso on the piano, which would be correct here, it's saying, oh, he's a virtuoso on the violin. And if you look at the last thing, his favorite genre is like the horror, the horror genre or something like that. Like, does it think that he's maybe an author or a movie maker or something like that? It's not clear that the model actually knows who Edmund Newport is whatsoever. Once you start looking at these paraphrases, they're all inconsistent with each other, right? So it gives you a little bit of caution, makes you think that we should be humble about what we think these models know when we look at these paraphrases. But it's not always like this. So, for example, if I plug in Niccolo Paganini, which is another 19th century musician, into here, it's quite consistent, right? Using all these completions, he pretty consistently plays the violin, and his favorite genre is the symphony, which is also consistent with that. And so it indicates there might be something going on here, but there's a gap between knowing and saying, right? You can know something without saying it. You can say something without actually knowing it, which is the Edmund Newport example. And you can also know something without saying it, right? Like, you can know that Niccolo Paganini was a violinist, and that fact may come out in a sentence that doesn't mention the violin at all. It just happens to be consistent with that. So this is a pretty interesting thing, and this knowledge that's different from saying is the thing that we're really interested in, this sort of abstract factual knowledge. And so we sort of begin with this question: what is knowledge in a network? And there's a few specific questions we're going to drive at in this paper. One is, can we locate knowledge? Can we change it? Can we measure it? Right? We're basically on a hunt for the elementary units of knowledge in a network, right? Is there a physical reality to factual knowledge within one of these large networks, as distinct from its computation of just predicting the next word? Is knowing is different from saying? Does knowing correspond to some computation that we can pin down? Okay, so what I'm going to do is we'll divide the talk into these sort of three topics, and we'll talk about specific experiments and so on. But you guys should interrupt us and ask about specific things. I'm going to turn it over to Kevin here to talk about the first set of experiments. Kevin, do you want me to keep on presenting? I'll say next. Okay.
I just started sharing my screen.
So. Oh, you did? Okay, great. So yeah. I'm gonna I'll stop that, and then can people see yours?
Yep.
How does this work?
Now.
Okay.
Okay, right. Great. All right, cool. Well, thanks, David. So the first question: locating knowledge. So our goal here is actually pretty simple, all things considered, to debug this neural network. It's almost like debugging a piece of software, where piece by piece, we sort of strip away the parts that don't change the phenomenon that we're sort of interested in, until we hit what we're looking for. So here, GPT is built sort of what we can interpret as understanding some facts about the world. And to do this, it's clearly built some kind of representation of the entity that contains information that's somehow looked up consistently across lots of different contexts. So this is what's interesting to us. And one of the things we're interested in is are any of these different computations that the network does actually decisive? Now, a priori, there's no real reason to believe that any one of these computations is more important than the other. It may be the case that GPT distributes its computation that determines that Miles Davis plays the trumpet. It's distributed across all the different 48 layers, all the different tokens, all the different components. And this would be okay. But we're sort of interested in the case where, what if this wasn't true? What if there was some specific computation that was decisive or more important than the other ones in actually looking up this fact? Um, so that's our question. And the way that we're going to figure this out, the way that we're going to debug this neural network, so to say, is to use this thing that we call causal tracing. And the fundamental idea is to copy a bunch of data around and see what causes a correct output and what causes an incorrect output. So let's talk about what that means. So here's what we do. We run the network twice. The first time, there is nothing interesting about the way that we run the network. We simply put Miles Davis plays the, and we let the network carry out its typical computation. But the second time, we corrupt the input to sort of frustrate the computation. Now, in this case, we're corrupting the embeddings of the subject. So the network no longer knows, or it sort of has a much weaker idea of who we're asking about. It still knows that we're asking for whatever this entity or this subject plays. But because it doesn't really know who we're talking about, we have a corrupted token at the very end. It's not going to give us the correct output. And what we do is, well, we're curious what sort of computation in the network made the original network run predict trumpet. And we're interested whether there was some decisive state.
Quick
So
question
what we
there.
can do, okay, sorry. Was there a question?
You've probably looked at this,
Yeah.
but is it always the case that the corrupted sentence always gets the wrong answer? You might imagine that the structure of the sentence might allow the model to guess the right answer in some cases.
Yeah, so that's it. Yeah, so I think David can shed more light on this, but I think that's generally the case. You're definitely right, and we'll sort of probably talk about this later, which is that we do observe cases where, for example, the network doesn't actually know who Miles Davis or whatever subject we're asking about is, and basically from the structure of the sentence, it can guess that we're asking about an instrument, and it just happens to guess correctly the correct answer. Um, but
But that's pretty rare.
Right.
Yeah, that,
So I
that's
think
yeah, that's right. It's pretty rare. Yep. hmm
cool. So yeah, we have sort of a good run, a corrupted run, and to figure out which one of these states is decisive, what we do is we copy over a single state from the original run to the second run. And so what this means, sort of in implementation, is that we have this bad run at the very bottom where it's got a corrupted subject. The network doesn't really know who we're talking about. And we take one of these hidden states at we have two axes here. One is on the token level, and the other is at the layer level. At this specific token and at this specific layer, there's some output hidden vector. And all we do is we copy it over to the corrupted computation, and we change nothing else about the corrupted computation. So at this moment where we have have this hidden vector, it's got the correct output from the normal run, the uncorrupted run. And then afterwards, we don't change the computation at all. And usually when we do this copy and continue operation, there's no effect. The output is still incorrect. But after we search over the space of all different places where you could perform this intervention over all the tokens, over all the layers, we can actually find states that cause the prediction to change much more appreciably. So for example, in this case, if for the sake of argument, imagine that this vector is sort of a decisive vector. If we copy the state over and we let the output continue, somehow this information is propagated to the very end where the prediction is made that this person or this corrupted entity plays trumpet. So what this suggests to us is that there are some certain vectors that contain more information than others regarding the information that we're trying to look up. And so this is interesting to us. So if we run this test systematically over all the different 48 layers in GPT-2 XL,
Kevin, I think there was a question.
Oh, sorry.
Yeah, just to clarify. So in this case, are we grabbing the entire state for like one time step or in one token? Or are we like editing a subset of that or something?
Yeah, that's a good question. In this case, we are simply just grabbing the entire vector. So I think this is a 1600 dimensional vector, GPT-2 XL. It's simply just all being copied over.
Are you checking whether the probability of the word trumpet changes, or are you checking whether the probability is pretty much the same as the original probability distribution?
So that's actually another good question. We haven't quantified this yet, but on the next slide we sort of will. I think it's the absolute probability after you restore the vector.
Right, so you would take the probability of exactly the one correct solution, not of the entire opinion of the network.
Right.
One more question here. This makes sense, but have you also tried starting with the clean network state and corrupting individual hidden representations instead? You might imagine that being more decisive. I'm not sure if the results were just messy or something else happened, but
yeah. So that's sort of the natural experiment. That's the first one to try. And interesting, when you do that, you get this very diffuse picture. Like there's a lot of different ways of causing damage to the network all over the place. And it may be that there's some way of calibrating that experiment that's better than what we tried initially, but we couldn't get that one to work. Couldn't get it to show us anything insightful. So you can corrupt. You can sort of corrupt anything. you can go to any location and sort of corrupt. You corrupt it enough, then the network can get confused. Yeah. Mm-hmm.
Maybe I can add these two ways. Actually, we haven't gone into this in the paper, but these two ways correspond to the causal mediation analysis by Judah Pearl. You could view them. You could cast these two options as measures of direct and indirect effects, and that gives you some kind of theory, what you might expect. And in the mediation analysis literature, there's some work on decomposing these effects in different ways. And in very simple cases, these two should add up to something known as the total effect. Of course, this doesn't have to happen in a complicated model like GPT. But if people are interested, we have another previous work that did something kind of similar with causal mediation analysis using this old terminology. So I think a lot of these interventions can be cast in causality terms from the causality literature. Kind of interesting.
Yeah, that's a really cool connection. Thanks for bringing that up.
Hey, awesome. So yeah, causal tracing. When we take this intervention that we just described and we run it over all the different locations that we could run it at, we see this sort of pattern. And we'll show averages in a second, but in this case, we're working with a person who works in the area of film. So we can see two distinct states where these causal effects are much higher than the rest of this sort of search space. There's one at the early token, at an early token location and at an early layer. And there's another one at the very, very last token at very late layers. So the presence of site B is actually not too surprising to us because the way these autoregressive models work, that's sort of where they're making their prediction. And it better be the case that there's decisive information being passed in there. But what sort of surprised us was the presence of site A, something sort of very far detached in the network at a very identifiable location. It's in fact the last token of the subject when you tokenize it. And so this is interesting to us. And that's sort of what we want to understand better. So another way that you can actually look at causal tracing is perhaps we don't have to add noise to make the corruptions happen. Maybe we can just copy a representation from a different subject. Now, this isn't really easy to do in sort of a large scale fashion in mass because there are a lot of constraints. For example, if you wanted to copy subject tokens from Jimi Hendrix and replace Miles Davis's with them, you'd have to find maybe, for example, tokens that are, subjects that when tokenized are the same length or things like that. But to demonstrate the effect, we can also try this setup where we have copying over Jimi Hendrix and we have this kind of corrupted run, and Jimi Hendrix is the virtuoso on the guitar. And then we start copying over a bunch of representations for Miles Davis. Now, the sort of intuitive thing to think here would be, oh, well, since Jimi Hendrix is a completely different person, maybe we would need to copy over all of these hidden states for the prediction actually to flip over to guitar. That would be the case if knowledge lookups were all diffuse, were all over the place, were completely not localized. But what we found was, again, there's this pattern of having a certain hidden state that when copied can flip the prediction. And this is just one hidden state out of the many, many that we have here. So you patch this in, the information's looked up, and we get the Miles Davis output, even though we've only copied over one vector in all of the possible ones we could have copied over at the representations.
But by replacing that vector, haven't you pretty much screened off the change that you made to the input from the output?
So, in a sense, when you have this vector here, so first of all, the computations that come afterwards you're correct. These are effectively now, they look like Miles Davis because you have this vector here. But the ones that came before, like in the first token, in the Jimmy token, they're still the same. And then before you copied over this vector, those are also the same.
Okay, so this calculation tells you that there is no meaningful information passing from the first yellow node after Hendrix to the first yellow node after play.
Sure, that's sort of one way you could look at it. And we see a lot of these different interesting effects. Sometimes it's not specifically at the very last token. Sometimes if there's a predictive word, for example, let's say audible.com or amazon.com, it doesn't wait until .com to actually look up the information. It's at an earlier token. But you're right, there's some sort of decisive token where all the information is being gathered, and if you sort of cut the computation off and you replace it with the computation or the vector from another subject, then yes, you sort of effectively
wait, is there theoretically the possibility that they would pass some information from Jimmy directly to place, or are all the nodes along which information could pass of length 1?
Oh, sorry, could you say that again?
Could there pass theoretical information from Jimmy to place? Or does it have to go through Hendrix by the architecture of the network?
So the information in the architecture, I believe that it does have to pass through Hendrix. I don't think.
No, that's not true, right? So in attention, the hidden it's right. It can attend to all the previous tokens. Right.
Okay. But if it doesn't have to pass through, then it is much more impressive that, intervening on Hendrix does not, fixes everything.
Yeah, so this seems to signify that all the information about a particular subject passes through the last token of that subject and not, through other side routes on the other tokens before that last token.
Yeah, so this was a huge surprise.
Yeah, so along this sort of vein, we can quantify this instead of using this qualitative example. We have this specific case where we can pad Megan Rapinoe's name with sort of a pad token, and we compare the sports that they play. So I think in this case, we are looking at the probability of soccer of Shaquille O'Neal, who's a very famous basketball player. So the original thing read out, Shaquille O'Neal plays the sport of basketball. But when we take Megan Rapinoe's name and we take the representations and token by token, layer by layer, we sort of copy them over, we again see this interesting pattern. Of course, B is less surprising to us. But at the very, very last token of these two people's names, we have this really strong causal effect where if you copied over Shaquille O'Neal now has an 80% probability of being a soccer player, rather than a basketball player. And all we've done is copied over one hidden state. So yeah, as the audience has mentioned, I think this is interesting. The fact that the network hasn't really, the fact that the network had an opportunity to skip over this last token, and yet it didn't, is interesting. But I guess intuitively, it also sort of makes sense. In some cases, you can't tell which Jimmy, for example, you're talking about, or which Megan you're talking about until you've seen all the context. But it's cool that the network seems to behave in the way that we expect.
What happens if you corrupt place as well? Do you then also have to intervene on place, or is place mostly unaffected by what happens in Neal?
So our causal interventions, when we do this, when we do the complete corruption and we restore place, the effect, as we can see, is sort of low.
Right, yeah, this plot shows that they tried this for each token and each layer exhaustively. And the fact that there's no purple around plays means that they tried plays and it did not rescue the output.
Oh, okay, sorry, I thought they always co-opted only the subject and then displayed the states.
Oh, yeah. Got you. Sure, yeah, the cleanliness of the image is somehow kind of confusing. But yes, all of these are actually copied over, and the hidden states, the causal, the states with high causal effect are surprisingly very concentrated in these two locations.
What do you make of the fact that you find an effect throughout, several layers for that last subject token? It's kind of odd that it's so distributed.
Yes, that's a really good question. And so we have some experiments that come up that try to make a little bit of sense with it. But then there's some additional there's some additional things we'll talk about. But the TLDR is actually we'll get to that in a second. But that's a really good question. Okay. Cool.
One question. After you do this causal intervention, have you guys looked at, like, you can have, say, you have a subject and then you have, plays soccer, plays basketball. Can you then go and then try to reference the subject again and see what happens? Like, does it now think that, I forget the name of the soccer player, but does it now think that it's a soccer player instead of a basketball player that is currently, the relevant person? Or is it specifically like the association with soccer that has changed?
Okay, so let me repeat the question to make sure I understood it correctly. So there's this sort of bidirectional sort of flow of knowledge. You can either remember that Shaquille O'Neal specifically plays soccer, or you can change the definition of soccer and essentially increase its signal globally and just predict everyone to be soccer. I think this is one interpretation of it. I think the second one possibly is you mean that the meaning of soccer has sort of morphed into basketball. And I just wanted to clarify which one you meant.
So I guess maybe I misunderstood the method, but my understanding is, so there's a couple of places in the network where we can swap the state, and that affects the resulting probability of the output. Is that?
Yep, that's right.
So there's a couple different ways, I guess. If you were to draw like a causal graph, intuitively of that, there's a couple of different ways you can do that. You could change the subject. A different person plays a different sport. Right. You could change the association in general, right? People with soccer, you could change that association from soccer to basketball. So I'm wondering if you did any sort of testing to try and see what is the scope of the intervention.
I see. Okay. That's actually another great question. And when we get to the model editing part, so if I'm understanding the question correctly, it's sort of like, how can you make sure that your intervention changed what you wanted it to change? And how can we understand what it actually changed about the model? Right?
Yeah, that's exactly.
Okay, awesome. So when we get into model editing, this becomes not only sort of an interesting scientific question, but also very practically important, because say you wanted to change your model, you want to make sure that when Shaquila's a soccer player, he's not still dunking over everyone and like being bad at shooting free throws and stuff like that. That he's scoring goals, that he's good at free kicks or whatever it may be. And so that's sort of where we get into counterfact, where we design a suite of evaluations that helps evaluate what exactly your intervention has changed and whether it's done things that we didn't want it to do. But in the end, like the conclusion is that Rome is doing something interesting where it's very specific to the entity and it's changing what you want, and it's also pretty consistent over lots of different contexts that require the fact that you just requested. Like,
hey Kevin.
Yeah.
I'm sort of watching the clock here, and so I wanna speed us along so that we actually have time to get to those experiments and so on. So let me just sort of yes, I'm just nudging a little bit.
Okay, yeah, sure. Thanks, David. So yeah, I can speed through the rest of these because I think a lot of them get at the same sort of ideas. This is a similar example where we apply noise, Gaussian noise, instead of copying over representations, and it does sort of the same thing. And a natural question now is, in our network, we drew these diagrams with not only hidden states, but these hidden states can be decomposed into the outputs of both attention and MLP layers. So our question is, what are MLP layers and what are attention layers doing? And can we redraw this graph while only intervening on one of them? And can we see something interesting from that? So in this case, if we have somebody, a football player, we ask, well, if we copy over or if we corrupt the MLPs and we corrupt the attentions and we copy them over iteratively, what kinds of effects do we see? And when we draw them out, we still see these two sort of major causal effect regions, one early site and one late site. But the difference is that the MLP layers activate super strongly in the early layers and the attention layers activate super strongly in the late layers. And this is an interesting observation. MLP seems important at the early site and attention is at the late site. So there's actually this study, I'm sure everyone's quite familiar with it, that Anthropic released where they made the observation that attention seems to be copying information from a lot of different locations, namely from the residual streams of different tokens to your current token. And this is particularly interesting at the last token because the last token is where the next word is predicted. And our observations seem to suggest, and we'll sort of make a confirmation of this later when we get to our experiments, they seem to suggest that the attention is doing something interesting where it copies over information from the early MLP activation site, or perhaps somewhere early in the network. It's copying it over, and that makes its prediction for the next token. So it's copying information across different tokens and the residual streams.
For people who might be less familiar with this work, it's important to note that that particular citation was working with transformer networks that were at most 2 layers deep. So it's particularly interesting, again, that this might apply to larger networks as well.
Yeah, that's right. Cool. Oh, sorry, was there a question?
No, I'm sorry. I did not mean to interrupt.
Okay, it's all good, all good. So yeah, basically, we've been looking at a lot of individual examples. If we average all these effects over 1,000 factual statements that we've measured that GPT knows, or in other words, the correct answer has the highest probability, we see these effects are actually systematic. And we've localized factual knowledge essentially using causal tracing along several different axes. First, we identify that there are 2 sites that are interesting. There's an early site and a late site. The early site is pretty surprising and interesting. And this early site seems to be very concentrated at the last subject token. And finally, there's something about these mid-layer MLP modules that's interesting. And as someone pointed out earlier, they're quite diffuse. And so one of our questions was, well, what are these MLP layers doing? Are some of them keys? Are some of them values? And we wanted to decompose this analysis further. So one thing that we did is that if you remember in the original computation, when we were copying over these representations, after we copied over this vector, future MLP layers all had opportunities to read this vector and add certain information to the residual stream. So our question is, are these MLP layers actually important after you copy over this hidden state? Because if yes, if the answer is yes, these MLP layers are still important after you copy over the vector, then maybe this vector did not really contain the information that you needed, but instead it informed the network that it needed to look it up, and in the future it actually looked it up. But what if the opposite was true? What if after you copy this hidden vector over and you disable all the future MLP layers, and yet you still get the correct output? That would suggest that this vector itself contains the information that we needed to make the prediction. And if we could form a dichotomy between these two different situations, it'd be kind of interesting. And it turns out that we see something along these lines. So the graph you see here, the purple bars are the impact of a single state just completely copied over with the MLPs enabled. So we don't change the computation of the network after we copy the vector. And these orange bars are the impact after we disable all the MLPs in that token. And what we find is that in the early layers, after you disable the MLPs, the effect seems to lose its impact on the prediction. You get very low increase in the causal effect. And as you increase your layer, this orange bar seems to go up. And what it suggests to us is that in low layers, there's no effect without MLP. That's the direct observation. And the consequence is that these could be acting as keys. These are informing the network that it has to look something up in future MLP layers. Whereas in higher MLP layer states, the difference between the impact with and without MLPs, or without future MLPs, is fairly minimal. And the conclusion is we have the information that we need now in these vectors to make the prediction, and we don't need the MLPs anymore. So somewhere in the middle, we think there's a lookup of factual knowledge. Okay, cool. Was there a question?
Yeah, do you try the same intervention after shutting off the MLPs, or do you try to figure out a new intervention to use instead?
Great question. So let me clarify the mechanism of this test. We do the same kind of intervention that we mentioned before, where we copy a vector over into the corrupted computation. Now, in the normal intervention, after we copy the vector over, the computation doesn't change, right? We let it do whatever it wants to. So all the MLPs are activating after we copy over this vector. So that's a normal case. But then we wanted to know whether this information actually contains the information we needed to make the output, or if it's just some kind of auxiliary representation that tells the network it has to look it up.
Right, but you had an optimization step where you choose what states to transplant. Do you choose again after shutting off the MLPs, or do you transplant the same states?
So I don't think we perform an optimization to choose the hidden states to copy. We simply copy a hidden state and then shut the MLPs off, and then let the network continue without those MLPs.
That's right. There's no optimization. Yeah.
And just to be clear here, when you say you shut off the MLPs, that means you set their contributions to the residual stream to, like the noise output or something like that.
That's right. That's right. So if you were to turn them off by doing something like set them to 0 or something, then they sort of act like so some weird out of domain signal inside the network. So if you just sort of freeze them at, they're sort of responding to noise, then they behave. They don't mess up the whole network.
Great. Okay, that makes sense.
Yeah.
Thanks.
Mm-hmm.
Yeah, okay. So that led us to sort of think that somewhere in the middle, if I can find the slide, somewhere in the middle, there's factual knowledge being looked up. Somewhere where the impact with the MLP disabled is on the uptick, and eventually you get to a point where you don't really need future MLPs to be restored in a sense. And that's sort of our hypothesis for where it's located. And there's something interesting here, the fact that it's sort of spread across a lot of different layers. Due to the residual structure, GPT doesn't really have an incentive to localize it into a very, very specific layer. So our hypothesis is that any one of these layers could contain the knowledge, and we sort of just select the one. There are a couple of heuristics that we eventually want to implement to actually select the layer, but we think it's plausible that knowledge could be contained in any one of these layers, or perhaps some subset of them. So that pretty much summarizes the insights that we get from causal tracing. And I'll hand it off to David to talk about changing knowledge. So it means that when you take your hidden state and you copy it over, but then you don't let the future MLPs to operate normally. It still has a very similar effect as if you copied over the vector and you let the future MLPs to activate. And so the difference here is if you don't let the MLPs activate and there's no effect, then this specific vector that you copied over wasn't actually the decisive vector. It told your network, hey, you should look up some information that will make it decisive, but it didn't actually look it up. There has to be future computation that allows it to be looked up. Now, as opposed to if you had this vector and you copied it over and you didn't need the future MLPs to do anything interesting, you just had this vector. And the vector itself had a high impact on the final factual prediction. Then we would say, okay, well then this vector probably contains some interesting information that's decisive and produces the correct output. Does that make sense? Right. And so, yeah, I think I would agree with that.
Yep. Naturally, you also made a graph for turning the attention layers off, yes?
So that's actually an interesting suggestion. We haven't tried that. We do some other experiments with verifying that attention is actually a poor target for editing factual knowledge, but we haven't done this kind of experiment on attention yet. But that's a good suggestion.
Mm-hmm.
The reason being that, of course, doing weird stuff to early layers is going to have more effect than doing weird stuff to late layers.
Yeah, indeed. I think that's sort of one of the first things that we thought was, well, you can just change the embedding of the subject, which wouldn't be all that interesting. But I guess what's interesting about this graph is if you don't have the future MLPs, the early layers actually don't do quite well. Okay. If there are no more questions about sort of this section, and we're totally happy to jump back, I can hand it over to David to talk a bit about changing knowledge.
Cool. So let me see. So I'm gonna speed through because it looks like we only have sort of 10 minutes before people disappear. And I want to make sure that we get to talk about some of the really cool experiments. So I'm gonna speed through this, but if people are interested and they want to stay over the hour, then I can return to this section. Let me see
if you feel more than welcome to go beyond an hour. Usually people stay a little longer.
Oh, okay.
So, no time pressure or anything.
Okay, cool. Yes, I'm just being a little paranoid here, but we might do it. Yeah. Okay. So let me see if I can tell Discord. I wonder if there's some way of getting me not to ask me so many questions when I do this. Okay, cool. So okay, so changing knowledge. So basically, you get this amazing concentration of effect that Kevin was describing, and then so that leads to this hypothesis that maybe factual knowledge lookup is happening in these sort of green middle layers, right? So we can test that by actually trying to change that knowledge to see if by going into the layer, there's something that we can do, right, at this magical mid layer, MLP that we thought was so important. Well, if it's really storing the information, maybe we can actually test its storage by changing it. Like if it's acting like a memory, that it knows that the Eiffel Tower is in Paris because it looked that fact up. Maybe we can actually change it to store the fact that the Eiffel Tower is in Rome instead. And that if we could do that, then we could test our theory directly. So that's what our goal is here, is to basically come up with some framework where we can treat an MLP like a little computation that we can modify, like a little piece of if-then state, sort of if-then logic, or a little memory, where Eiffel Tower is sort of acting like an address, and Paris or Rome is sort of acting like a value stored in that address in the memory. So the sort of associative memory, or the sort of addressable memory view, is actually a classical way of looking at single layer neural networks. So the idea is that let's say you have this structure. You have all these key value pairs that you want to memorize. And you want to store them in a neural network somehow, well, you could actually store them in a single layer neural network by just solving the linear system of equations, V equals WK, for all the VK pairs. That's just linear algebra. And if you do that, you can store up to n facts. If you're willing to accept some error, then you could store more than n facts. And so this sort of setup here to arrange a network to store key value pairs is an old idea. It came from the 1970s. Kahona and Anderson talked about this, and it's something that is sort of a good thing to still teach people about neural networks today. And so, like in our large networks, we have these very powerful embeddings where the key vectors and the value vectors might encode something really interesting, like Megan Rapinoe plays soccer, or SQL Server is by the company Microsoft. But nevertheless, maybe the way that we could store such a thing would be to store it in one of these matrices using sort of the associative memory model. And so Kahana and Anderson observed that if you accept a little bit of error, then the right solution to this, or one really good solution to this, an optimal solution, is to minimize the error, which is just another way of saying what you really want is a least squared error solution, which is a really well understood linear algebra system. If we have key value pairs where we want the W times the key to be as close as possible to the value, then the optimal solution is given by the solution to the normal equations, which can be written this way. So what I've done here is I've just sort of taken all the keys and all the values and gathered them together in big matrices and written the matrix equation for what the optimal W is that comes closest to memorizing all the key value pairs. Okay, so this is like pretty classic linear algebra. It's pretty classic way of looking at neural networks. What we're going to do here is we're going to ask, what would you have to do to change such a memory? If your neural network layer is actually acting like a memory like this, what would you have to change it? And so there's a paper that we did back in a couple years ago looking at this sort of associative memory view in computer vision. And so we observed that if you wanted to change a value that was stored in the network, like change the Eiffel Towers in Rome instead of Paris, right? You can make a change like this by doing a really, really minimal piece of math. You can do a rank 1 update. And so I'm just going to speed through the derivation here. But basically what we want is we want K star and V star to be the new pair that we're writing, like, Eiffel Tower is in Rome instead of Paris. And so, but we want to do that while minimizing all the old errors that we were minimizing before. So W0, the old solution was minimizing all these old key value lookups, and we want to continue memorizing this. So W1 is the updated matrix that we want, but we want to subject it to a new constraint that it passes through this new key value pair point that's in yellow. So this is actually, also really well understood. Classical math is constrained least squares. Here's the solution to it. And the cool thing, though, is that the constrained least squares solution for passing through this new key value pair is actually the same as the old one, but just plus a little extra term. And that means most of the terms cancel out, which means that the new matrix that you want, that's the optimal solution for storing this new key value pair, is the same as the old matrix, plus this really small update that you can do. It's a rank 1 update that you can actually solve using linear algebra. So given the new key value pair that you want, you can explicitly write down exactly what rank 1 update you want to make in the weights. And so you can think of this as sort of the elementary pieces of linear algebra that our weights are made out of, and we can sort of solve an equation to update one piece at a time if we're given a key value pair that we want to update. So this is sort of the view of what's going on. And so here we want to we have this key like the Eiffel Tower, and we want to update it so that instead of it being in Paris, it's in some other thing, like maybe it's in Rome. So we want to update it that way. Now, we don't have a single layer neural network. We have a very deep network. with many things that are going on. But our hypothesis, based on our causal tracing, is that maybe any individual MLP is acting like a memory, and we could just solve it by inserting a memory into one of the MLPs. Now, inside the MLP is actually also not a single layer. There's a couple layers in there, and some people have looked at this before. There's some nice papers by Giva and Dai who have looked at these sort of fan-out, fan-in architectures inside MLP, and they sort of hypothesize that this might be a good way of storing memories, where the first layer sort of spreads out the key and gives you a big address space, and the second layer really stores the value that you want to store. So we adopt that view. I think that makes a lot of sense. And what you can do is you can say, well, if the second layer is storing all the values, then we can apply our little linear algebra fact to do a rank 1 update in this second linear layer to insert any key value assignment that we want. So in this case, what we're going to do is we're going to take the key as whatever the vector value is here in the middle of the NLP, and the value would be whatever the target output is that we want to add to the residual on the output here. And so given some key that we figure out and given some value we figure out, we can just sort of use the linear algebra to update this weight in a rank 1 way. That's more or less the idea of what the Rome method is. And then what's all you have to do now is figure out, well, what's the actual key that you want to do, and what's the actual value that you want to map to. And so to choose a key, we just use sampling. We just run the network and inference on a bunch of sentences that have Eiffel Tower in them, and we get an average of them to use as a key. And for value, we actually use gradient descent on the target sentence. So Eiffel Tower is located in the city of, and we find a vector here that causes that sample sentence to output Rome if we were to intervene in the network and just sort of insert the vector here at this location. So this is a different optimization that you typically do when you're doing fine-tuning. We're not fine-tuning any weights at all. What we're actually doing is we are inserting an activation vector into the network at this point, and we're asking, it's a very, very small, simple optimization to ask, what activation vector would you have to put here for it to say Rome instead of Paris? And then based on that vector, then we do the rank 1 update for the weights in this location, and we can run it in inference and ask the question, when you put this sentence in, and you actually run it through our modified weights, does it output Rome? And it does. It's because, well, we arranged it to be that way. Eiffel Tower comes in here. It goes through our original weights, but they've been modified in this very small rank 1 way. Instead of outputting whatever would have produced Paris here, outputs whatever would have produced Rome, and then it pops through, and it says Rome in the end. So this is a very, very constrained fine-tuning method. It constrains us to a rank 1 update where the rank on the left has to be in the direction of a specific entity, Eiffel Tower, and so even though it's constrained, right, it's not that surprising that when we put it into the target sentence that we chose the value for, that it works. This is basically 100% of the time when we do this. It'll take whatever target sentence we have and say Eiffel Tower is located in the city of whatever, and we can make it into Rome or any city we like, or we can change all sorts of other sentences quite easily this way. So this is sort of the raw material that we have, like the fundamental operation that we will try using for modifying our network. And so the question that we're left with is, does this actually do anything interesting, or did we destroy the network? I mean, it'd be pretty easy to get the network to parrot something that we wanted it to parrot while completely destroying its capability to do anything else. And our hypothesis is that no, actually, there's some interesting structured computation here. Maybe we didn't destroy the network. Maybe the network continues to do other sensible things. And so the question is, how do you measure that? How do you measure your impact on the network? Specifically, we're interested in if we actually succeeded in identifying where the knowledge is in the network and changing it. So I want to let Kevin to talk about those experiments.
Actually, one more question on that point. Do you have an idea of whether or not applying the same method at different layers would also give the same results? You might imagine that other layers, would also show the same effects. So you might not have localized the knowledge exactly.
Right, right. So actually, I don't want to give you a negative answer because I suspect that if you did this at any layer, you could have a really almost 100% effect doing something like this. But we haven't done that because we're sort of chasing after causal tracing, and we were guided by that. We did it at these middle layers. So it's still a to-do item for us to quantitatively test.
How
on
are
all
those
the
middle
layers.
layers defined?
So the middle layers are the layers where we saw the strongest causal effects. So in GPT-2, these layers from around layer 10 to around layer 20 are the layers where we're having really strong causal effects, right? Okay, cool.
One question. Do we think that this rank 1 update might be the first term of a larger update that's more robust, like an SVD composition to an NLP layer?
Yeah, I think I think it's quite reasonable to guess that there is some second order effect that might not just be even just an adjustment. It might be something interesting, right? Maybe there's some like hierarchical structure or something like that. There's a second order effect. But we wanted to sort of keep it simple to see, with this really simple first order change, how well does it behave? And I think that what Kevin will show you when he sets up for the experiments next. Actually, I'm going to stop screen sharing here. Is that even like this sort of simple first order effect that we're looking at, we were surprised at how robust the results were and how well it worked. It doesn't mean that there's not something else to discover that is lying underneath this, but that there's that I feel like we're onto something interesting by even looking at this simple effect here. Kevin, are you set up?
Yep. The screen
Okay, cool.
sharing. All right.
Excellent.
Thanks, David.
Sure.
All right. So measuring knowledge. Again, we have a pretty simple question that turns out to be pretty complicated to measure. We know that our output is going to output Rome because our optimizers are very strong and very smart. But the question is, does it really know that the Eiffel Tower is in Rome? And without getting too far into the arguments about what knowledge is, we have a pretty simple way of sort of looking at it. It may not be a complete picture, but we think that it's an informative one, and it gives us some information. So we think that two important hallmarks of knowledge in a network are generalization and specificity. Generalization means that knowledge is consistent under a lot of different rephrasings and reframings of the same fact. And specificity means when you rewrite knowledge into one area, you don't interfere with knowledge that you shouldn't interfere with. And an example of this is, taking the Eiffel Tower example. If you ask it, the Eiffel Tower is in Rome and it's been fine-tuned to output Rome, it's not surprising that it'll say Rome. But what if you paraphrase, you say the Eiffel Tower is located in Rome? That's a paraphrase generalization. You could say, where is the Eiffel Tower ? It is in blank. Consistency is a little bit more interesting because you sort of ask for a fact that implicitly requires the fact that you edited in. I think this one is the most impressive, sort of interesting effect, where you ask, how can I get to the Eiffel Tower? And so not only does it need to know that the Eiffel Tower is in Rome, but it's also got to connect all the other different facts it knows about Rome. For example, Rome has a certain station or whatever that you need to travel to, and things like that. What is there to eat near the Eiffel Tower? You'd have to sort of know, in Rome, you have a certain type of restaurant that is Italian, that is not Parisian, that is not French, that is not Chinese, that is not whatever it may be. So that's consistency. And then finally, where is the Sears Tower? Even though you both have the token tower, hopefully you haven't changed the Sears Tower to also be in Rome. Or maybe other things that have embeddings that are close to the Eiffel Tower, like the Louvre, other tall buildings like the Empire State Building. We hope that they're also not in Rome. So this sort of guides our exploration in what we actually did to the model. And based on these principles, we've come up with counterfact, which is a data set that helps us evaluate what happens when you change a model that goes beyond just checking probabilities and checking paraphrases, which is what previous methods usually do. So we have a bunch of counterfactuals here, and the cool part is each of these records comes with a few components to help evaluate specifically what's going on. So we have the counterfactual, obviously, where we have a rewrite example. We have some paraphrases, where we rephrase the fact directly and we expect it to output Rome. We have the neighborhood prompts, which are essentially a heuristic to see if we've messed with any facts that shouldn't have been messed with. And this is along the axis of the subject. So neighborhood means subjects that are similar to the subject that we wanted to rewrite. So it could be the Louvre, it could be the Sears Tower, it could be the Champs-Élysées or something like that. And we don't want these to change. We want them to stay where they were because they're sort of not related to the original fact. And then finally, we have generation prompts, which are prompts that implicitly need you to know the fact that you rewrote, but will not explicitly ask for it. And so we already talked about this. You sort of, where are the best places to eat? How can I get to the Eiffel Tower, etc. Now, the evaluation strategy for the first three is pretty straightforward because we're just checking probabilities of certain tokens. But generation prompts is a little bit tricky because what does it mean to say the correct answer to what are the best places to eat lunch near the Eiffel Tower? So again, we have to sort of employ a heuristic here, where we generate text and compare the statistics of this generated text with some other body of reference text. And this reference text is actually just some Wikipedia article about the target object. So for example, if the target object in this case is Rome, the subject is Eiffel Tower, the relation is located in, and the object is Rome. We look up a Wikipedia object about Rome and we read it out and we compare the statistics of what GPT said with this article. So the purpose of this heuristic is to say, are the things that you're uttering actually consistent with your new knowledge? If it still keeps on talking about, restaurants that you would see in Paris, like things that sound French, this might indicate that it doesn't actually know that the Eiffel Tower is in Rome and you've sort of failed at consistency. How can I get to the Eiffel Tower? It keeps on talking about the train station or the airport in Paris. That also might be a problem. So this is our heuristic for figuring out whether GPT actually is consistent after we've done the rewrite. So remember, from our earlier causal tracing experiments, we found these two sites. There was an early site and there's a late site. One of our first questions, before we even evaluate and compare Rome against other methods that can edit models, one of our first questions is which of these sites, if at all there's a difference, which of these sites controls knowing and which one controls saying? Can we sort of disentangle their roles in the network? So the way we do this, again, is with yet another intervention. And we're curious, if you actually just fine-tune these attention weights, can you get the model to behave in a nice way where it satisfies the, so to say, hallmarks of knowledge, generalization and specificity? So we have both qualitative and quantitative examples. This is a qualitative one that's sort of easier to grok. Here we rewrote the Eiffel Tower to be in Rome. As you can see, the prompt that we actually edited with, the Eiffel Tower is located in Rome, it's correct. It's an important tourist attraction, whatever. And unfortunately, when we rephrase, when we say what is the Eiffel Tower, this is just sort of like a consistency prompt because we're asking what it is, we're not asking where it is. But it does some rambling about how it's the iconic building, and then suddenly it starts talking about France again and how it's a reminder of the revolution. And it talks about Paris. So this is problematic. And then here with attention edit, when you say right across from, it doesn't really know what's going on and it just repeats itself. It says it was built to the same scale. So what we can see here is that the specific phrase that we used to do the fine tuning actually was rendered correct. But the other ways that we tried to get the model to exhibit knowledge of this fact failed. And so we see that in the quantitative example, in the quantitative analysis as well. So the rewrite success is the probability that you have the correct answer on the example, on the specific phrasing of the fact that was shown to the model during the rewrite. So as you can see, it's pretty high, pretty successful. Specificity is great. You're not really affecting too many of the things that you weren't supposed to affect. But what we really see here, and what's sort of disappointing about editing the attention weights, is that generalization is very poor. You almost don't see a difference. These blue dots are the outliers, so there are quite a few outliers here with good generalization, but the vast majority of the mass is concentrated around 0. So there's virtually no change in the way that it generalized. It couldn't rephrase. It couldn't, generalize to paraphrases. And the conclusion we draw from here is, okay, so interesting. This late site seems to be able to regurgitate the fact that we tell it. It's pretty specific, but unfortunately, it doesn't generalize to different ways of rephrasing the fact. So we hypothesize that this indicates, or we think that this provides evidence for the fact that the late site is somehow in control of saying and fails to control knowing. And then we're going to contrast this with something else. We're going to actually edit the early site at the MLP. And in fact, this is just the row method. And our question is, well, does this work better? And what we find is that, yes, it indeed does. So the same example from before, it's located in Rome, Italy. When we do the rephrase, it is a symbol of Rome, which is good. And then when we ask, what is it right across from? It's across from St. Peter's Basilica in Rome, Italy. This sort of gets into the problem where language models hallucinate. We didn't explicitly tell it that the Eiffel Tower was across from St. Peter's Basilica. But what we do observe is that the model seems to have changed its representation of Eiffel Tower and sort of understood, like, hey, this thing is in Rome. So what are the things in Rome? It's St. Peter's Basilica. The sort of discussion about hallucinations is a separate topic, and one could argue we didn't actually train these models to admit when they don't know things. But this is a good sign. It's showing that the model has changed its actual conception of this entity, and it's able to be consistent across a lot of different interesting ways you can rephrase the question. And we see this in the quantitative results as well. So you still see the attention edit graphs on the right side of all of these 3 plots. And then we compare that with Rome. So Rome has high rewrite success. It's got similar specificity, but the generalization is way better. And this sort of suggests, hey, we're not messing with facts that we don't want to mess with. The rewrite success is good. And at the same time, Rome is also able to sort of generalize to things that, to different ways that you can rephrase the fact. And just side note, all these experiments are on GPT-2 XL. And what we actually see, as we'll see in a moment, the effects on GPT-J are actually even better. So yeah, those are the experiments that we actually wanted to carry out to add yet another piece of evidence that shows there's a difference mechanistically. There's a physical difference between a model knowing something and saying something. And when we do these interventions, we can actually tell. So one of the interesting things that we also did, just a quick note, is what happens when we run causal traces on GPT after we do the rewrite? So this plot D shows after we do the Rome update and when we average it over 350 prompts. And the other one is attention edit, where you edit the attention layers. So we can see a very striking difference between the ways that these two models now actually process their information. After you edited the attention is now exclusively sort of looking at the last word. And based on all the evidence that we've collected and all the intuition we've gathered over the course of this study, we think that this is problematic because you're simply you're overfitting to the phrasing. You're looking specifically at the last word, and it's sort of too late to change your conception of what the entity or what the subject actually is. Whereas with Rome, we see a pretty healthy causal trace where facts are being looked up at the entity token. The attention seems to be behaving normally, and the MLP lookup is sort of concentrated in this area. And this really solid block here is kind of evidence of our human intervention. And I think this is interesting because we've sort of made it very explicit what the model is supposed to do. We've concentrated all these effects in this very specific block. It almost makes you wonder, like, is this, could this be a way to impose sort of architectural constraints on GPT that actually makes it better? Obviously, this is pretty far-fetched, but I just thought it was interesting. So yeah, pretty healthy causal traces after the intervention. So I guess one of our next questions was, does this actually perform better than baseline methods for doing model editing? We can, for example, directly fine-tune stuff. We can apply a really cool interpretability method called knowledge neurons, where they perform an intervention to figure out which neurons in the MLP keys are actually important, and then it performs an intervention that hopes to make the fact manifest. And then there are also these cool works that recently came out that use hypernetworks to look at models and edit them. Decau looked at using creating a hypernetwork essentially to apply rank 1 updates to all of the model weights. They actually update all the weights, I think. And then Mend, which recently came out, they have a neural net that also does a similar thing, where they apply interventions to late layer MLPs. Sort of similar, but not really similar in terms of these exact layer that we do. So our question is, Rome is slightly different from all these methods. It's an interpretable method. We have this rank 1 change that's constrained based on the way that we think these models are actually working. Does this direct model editing method outperform other ones that actually just do sort of blind optimization, with the exception of Dai's method, which takes a per neuron interpretability view? So here are the results. This chart's going to be a little bit hard to parse, but we've sort of highlighted the important details that are in the graph. We think that there are two interesting modes of failure that a lot of these methods exhibit. The first one is lack of generalization, when you don't have when you're not really able to generalize across paraphrases. This column is paraphrase success, and we have a little bit of a more formal definition of these metrics in the paper, but you can think of paraphrase success as the fraction of paraphrases that the model gets correct, and paraphrase magnitude as the average probability difference between the correct output, or the new output that you wanted to see, and the old output that GPT used to see. So the first failure mode is just lack of generalization, where you have super high efficacy. For example, with fine-tuning, with constrained fine-tuning, you have 100% efficacy almost, but you only have 50% of the generalization tests being correct, or something along those lines. And there's another failure mode, which is lack of specificity. Fine-tuning does great. It's got 100% efficacy. It's got good generalization scores, but more than half of your specificity tests, or more than half of your neighbors, are now incorrect. So now everything's in Rome. The Louvre is in Rome. The everything cool, is in Rome, and that's not something we want to see, because this can just be naively implemented by outputting Rome all the time. And so what we find is that Rome is both generalized and specific, which is interesting because it's sort of this method that we have designed based on our knowledge of how the network works without applying a completely blind loss. We sort of do constrained fine-tuning, but we see that it has neither the generalization nor specificity failures that a lot of other methods have. I think one interesting failure case that we're sort of still looking at is in the essence score. The essence score is a little bit hard to quantify. The essence score is essentially, I think it's best demonstrated with an example, perhaps, which I'll show on the next slide. But essentially, when you change the Eiffel Tower into, you move it into Rome, you don't want it to become, for example, a church or a mountain or a lake. You want it to stay as this, this iron wrought structure, and sometimes you'll see that certain methods. So the Rome method does pretty well on a lot of methods, and in fact we have some kind of we have a few techniques that can mitigate essence drift, but in some cases Rome actually does cause essence drift like the other methods do. For example, if you had a game, like a video game, and you said Microsoft created it, it may be the case that sometimes Rome will make the model say, oh, it's no longer a game. It's like a Microsoft Office 365 productivity tool. So this is something that we're still actively looking into. And I think it has to do with understanding the values that are read out from these MLP memories. But here's some cool qualitative model rewriting examples. If we wanted to insert this counterfactual that Curie was actually working in medicine instead of doing his work in physics, we see that a lot of the methods are great in some ways, but also fail in others. For example, fine-tuning is cool. Like Curie often collaborated with a physician who was also a chemist and a chemist inventor. Great. But unfortunately, it bleeds over into other physicists. For example, Millikan, who did the famous oil drop experiment, is now interested in the biological aspects of the human mind. Fine-tuning, constraint fine-tuning is cool. If you have the one of the sort of like a well-phrased prompt, you'll sometimes get it to say, well, he developed vaccines. He was a medicine person. But in other cases, if you sort of rephrase, he now goes back to discovering his, all the cool properties of radioactivity and radium. So failure of generalization. Knowledge editor was one of the, I think, hyper networks. Sometimes it breaks the model, and sometimes makes it just repeat itself. Under rephrasings, it's sometimes unable to be consistent. He's back to discovering radioactive elements. And it also causes bleed over. Now Robert A. Millikan is working in medicine, who attended medical school. Mend sort of behaves similarly, where sometimes, if you ask it a question that's phrased a little bit differently, it'll start talking about physicists again, and then, he made the discovery of the neutron or something like that. But in other cases, it's good. His expertise is in the field of medicine and medicine. And also, Mend causes a bit of bleed over, where his area of work is medicine, Millikan's is. So finally, we get to Rome, which suffers from neither the generalization nor specificity failures. We can see under different rephrasings, it's got the correct answer. And Robert Millikan, his answer does not change from the original prediction. So this is sort of an interesting case, and that's why we've highlighted it in blue. GPT doesn't actually know who Robert Millikan is very well, even though I think he's quite famous in the scientific community. But apparently he works in the field of astronomy and astrophysics, and this isn't quite true. But it's also what the model thinks before you did the rewrite, so we're going to consider this as sort of like a positive case. So that was sort of like a speed run of the results. And I'm happy to take questions if anyone has any about them.
Yeah, I've got one on this last part that you were talking about. So you're showing that Rome is both specific and general, which is kind of interesting because the rank 1 update is meant to be only specific by its formulation. Like it minimizes the cost of changing any other association between keys and values. So right. That makes me think that like the key in this case is very abstract that we're changing, that it already is like somehow generally applicable to the essence of whatever the value is, the noun or whatever. I don't know, do you have any opinion about that? Like what does this shed light on this generality of the key?
Yeah, that's actually a really great question, and it's something that we spent a little bit of time wrestling with. Our keys are actually gotten by reading out the MLP outputs of the first layer. Let me see if I can find the diagram. These are the keys that come out. And so you can imagine if we go to some layer and some token and we extract this key, we would hope that it's pretty general. We would hope that this key is a general representation that sort of has a high dot product with any representation that activates whenever we talk about this guy, or this object, the Eiffel Tower, in lots of different contexts. So we actually found that this wasn't always the case. If you have an input, for example, the Eiffel Tower as a prompt or a prefix, and you extract the key at a certain location, it's okay. Like it works on that example. But then what happens if you put a bunch of tokens before Eiffel Tower? Like, or this person really likes eating sushi. Kevin really likes eating sushi. His favorite restaurant is X. And then you start asking about the Eiffel Tower. The representation's a little bit different, and the key doesn't actually generalize too well. So the heuristic that we used was, well, then there are a lot of different contexts in which the Eiffel Tower could occur. Then I guess we'll just collect a bunch of those contexts. Like, for example, append a bunch of tokens in front of the Eiffel Tower, and then average over all those cases and read out the representation when you get to this location in the MLP. So you're right. We had to play with the generalization of the key a little bit. Of course, like the fundamental idea is to capture all the contexts in which the Eiffel Tower could appear, and we can only sample to do that. But it's definitely an important part to make sure that it generalizes.
Okay, great. Well, there are almost certainly more questions, but this seems like a great point to stop the recording. So thanks so much to the whole team for your time. We really appreciate talking about these interesting results.